Chapter 29. We have 3 problems here in our review, so let's get right at it. A laser beam strikes a tungsten surface and electrons with kinetic energies ranging from 0 to 0.50 electron volts are emitted. What is the frequency and wavelength and vacuum of the laser light? So I'm going to start by just drawing a picture. So I have, here's my tungsten, and I have my laser light coming in. So this is E equals HF. And that light comes in and it finds this lonely old electron down here. And the light is absorbed by the electron, 1 photon energy. And the electron with that energy goes off, and it may bounce a few times, but it comes out of the surface. It comes out of the surface with kinetic energy ranging between 0.500, I gave electron volts. Now, how could it be ranging? Well, if it comes straight out without hitting anything, then it would be at the top end. But if it hit things, it's going to lose some energy, so that's how it can have lower energy. Now, for energy conservation, I'm going to have the energy of my photons completely absorbed by the electron. So initially, the electron had a kinetic energy equal to the energy of the photon. So I'm going to have HF, the energy in, is equal to the kinetic energy. I don't know how that happens. The kinetic energy of the electron, but then it takes a certain energy to escape, minus the work function, minus the energy to escape. So kinetic energy should equal that's a plus sign there because it lost it. It went into that. Kinetic energy then is HF minus the W. That's where I should have had the minus sign. So my total energy in is equal to the energy that goes into kinetic energy and the energy that goes into the work function. And then there is the plus energy loss. So we're doing kinetic energy max here. So kinetic energy max occurs when energy loss is 0. So here's our equation to govern this, which is called the photoelectric effect. This was the proposed experiment from Einstein to show that energy comes in packets for light of HF. So I need to find first the work function for the tungsten. Well, that is just do an internet search, and when you find it, you find that the work function for the tungsten is 4.50 electron volts, roughly. Actually, roughly 4.5. So I really only need 1 sig fig there because my tungsten only has to the tenths. Now use energy conservation to calculate the relationship between maximum kinetic energy of an emitted photoelectron, the work function, and the frequency of light, then calculate the frequency. Well, I already found that, so now I just need to take this equation and actually solve for F. So take the above version. F is equal to the kinetic energy max plus the work function divided by Planck's constant. So kinetic energy max was 0.500 electron volts plus the work function of 4.5 electron volts all over 6.626 times 10 to the minus 34 joules times seconds. Now you see a problem. Electron volts for energy on top, joules for energy on bottom. So let's multiply by 1.602 times 10 to the minus 19 coulombs per electron. And then I will have a volt. Remember, 1 volt is equal to 1 joule per coulomb. So when I multiply by that charge of an electron, my electrons will cancel here and here. And then my coulomb and volt will cancel, and I have joules on top. And so it's going to give me my frequency in hertz. So when I pop that into the old calculator, I get 1.21 times 10 to the 15th hertz. So that's the frequency of this laser beam. Now, I also am to find the wavelength, so now I will simply take wavelength times frequency is equal to speed of light. Therefore, wavelength is equal to speed of light divided by frequency is equal to 3.00 times 10 to the 8th meters per second divided by 1.21 times 10 to the 15th hertz, and that's equal to 248 nanometers. Another way I could have done this that would have been quicker for me is because we know that wavelength is equal to 1240 nanometers times electron volts over the energy, then I just would have had 1240 nanometers times electron volts over 5.0 electron volts is equal to 248 nanometers. Same actual calculation. So that's the first one. Now this would be an application, not a synthesis. Second one, a laser beam from problem one. The laser beam from problem one is scattered off of an appropriate medium. When the scattered beam is deviated 30 degrees from the incident beam, what is the difference between the two wavelengths that will be detected? One is the original wavelength, and one is a Compton scattered, so a shift from the Compton scattering. Why would this laser not be a good choice for exploring Compton scattering? Well, Compton scattering, you have light comes in, it hits an electron, the electron scatters like this, and the light scatters like this. And we have a different frequency that light, so squiggly here. So that's the figure for Compton scattering, and then we have the equation that defines Compton scattering. I don't like that color. I want that color better. That says the scattered wavelength minus the incident wavelength is equal to Planck's constant over the mass of an electron times the speed of light times 1 minus cosine of the angle the light is scattered. So in this case, I just put my 6.626 times 10 to the minus 34 joules times seconds. Divided by the mass of electron, 9.109 times 10 to the minus 31 kilograms. Speed of light, 3.00 times 10 to the 8th meters per second. Multiplied by 1 minus cosine of my angle, which was 30 degrees. That was my scattering angle. And that gives me a scattering angle of, or excuse me, not a scattering angle, but a shift in wavelength of 3.25 times 10 to the minus 13 meters, or 325 femtometers. All right, that was also not a synthesis problem, but a more standard application. Now we do have a synthesis problem here, and of course this has more than one piece, more than you have in a synthesis problem. A collimated beam of 1,000 kiloelectron volt electrons, that is their kinetic energy. Their rest energy is 511 kiloelectron volts, so the total energy is 1511 kiloelectron volts. Notice its kinetic energy is very large. It's significant compared to its rest energy. In fact, it's bigger than its rest energy. So this is absolutely relativistic. You have to use relativity calculations when you're dealing with this. It goes through a slit that is 1 millimeter wide. When it strikes a screen 1 meter away, what is the minimum width of the central peak according to the uncertainty principle? For the work, assume the beam is traveling in the y direction and the split is measured in the x direction. How does this compare to the single slit diffraction? And there's the single slit diffraction equation. Now, let me start off with my picture. So I have a slit. And that slit measures D equals 1.00 millimeters is the size of that gap. And now I have a collimated beam. So my electrons are going like this. Find my X and Y directions. That's a right-hand coordinate system. That's why I put X down. So it's going like that. Then I have a screen that is out here 1.00 meters away. And my beam, according to relativity and according to waves, is going to expand. So even though it came in, what I would say is collimated, it's going to expand. And so what I'm going to be looking for is how big this is. So that's my physical relationship. It tells me to start by calculating momentum in the y direction. And so calculate that momentum in the y direction. I have E squared equals PC squared plus E0 squared. Well, I know that E squared is going to be the total energy, 1511 electron volts, kilo electron volts squared. And the rest energy is going to be 511 kilo electron volts squared. So if I solve that for PC, I have PC is equal to the square root of 1500 keV quantity squared minus 511 keV quantity squared, which gives me, what does that give me? 1422 keV for PC. That is, momentum multiplied by the speed of light is 1422 kiloelectron volts. Well, I'm going to want this in joules, so I'm going to change it right now into joules. So multiply again by 1.602 times 10 to the minus 19 coulombs per electron, and times 1,000 electron volts per kiloelectron volt. So I just want to get rid of the K. Cancel those E's. And then I want to divide everything by C. So I'm going to do this in a different color just so we see that I've done it. And I end up with my momentum in the y direction is equal to 7.60 times 10 to the minus 22 kilogram times meters per second. Come on, yes. All right, so we've got that momentum calculated. Huzzah, yay, another relativity problem, right? Well, no. Given that we don't know where an individual electron is passing through the slit, we can say that the position is the center of the slit, so the position we'll say is right here, plus or minus half the slit width. So that means my uncertainty in position is 1/2 the slit width, or 5.00 times, actually 5.0, times 10 to the minus 4 meters. So now using the uncertainty relationship, what is the minimum uncertainty in the momentum in the x direction. Uncertainty relation, uncertainty in x times uncertainty in momentum in the x direction is greater than or equal to h bar over 2 or h over 4 pi. So that means that solving for delta px, times 0 times second over 4 pi times 5.0 times 10 minus 5 meters. And my uncertainty in the x direction turns out to be 1.05 times 10 to the minus 31 kilogram times meters per second. 1.05 times 10 to the minus 31. Now looking at my picture, I have the momentum in this direction, that's Py, and I have my uncertainty momentum, my delta Px in this direction, so I can calculate this angle to right triangle. I have the opposite side and the adjacent side, so that means I can have tangent of theta is equal to delta Px over Py, or theta is equal to the inverse tangent of delta Px over delta P, not delta P, over Py. And so then I just put in those numbers. 1.05 times 10 minus 31 kilograms times meters per second divided by 7.60 times 10 minus 22 kilograms times meters per second. And that gives me an angle of, it's actually, to me, I wanted to use radians, but I'm going to use degrees. 7.95 times 10 to the minus 9 degrees. So that's the angle it makes. Now, if that's the angle it makes, now let's see what question, yeah, I asked for that angle. So the angle is 7.95 times 10 to the minus 9 degrees. It's a very tiny angle. Use trigonometry to find the minimum width. Well, if I want to do the minimum width, the width is 2 times the length from there to there. So using trig again, I'm going to have width is equal to 2 times the opposite or the adjacent side, which is 1.00 meters, times tangent of theta. Tangent of 7.9517. Yeah, 7.95 for us. That's a 7. Times 10 minus 9 degrees. And that gives me a width of 2.78 times 10 to the minus 10 meters. So the minimum width is 2.78 times 10 to the minus 10 meters. Now, we're going to actually compare this with what we would get from a diffraction. Now, we didn't do single slit diffraction this year, but the equation for single slit diffraction is you have minima at d sine theta m is equal to m lambda. Looks very much like the double slit experiment, except for now that's minima. And the if m equals 0, it doesn't work. It's for m equals 1, 2, 3, 4, not 0. So let's calculate the de Broglie wavelength. So the de Broglie wavelength says that wavelength is equal to h over py. So that's going to be 6.626 times 10 to the minus 34 joules times seconds over the momentum in the y direction, which was 7.60 times 10 to the minus 22 kilogram meters per second, which gives me a de Broglie wavelength of 8.72 times 10 to the minus 13 meters. Okay, that's a pretty short wavelength. This would work well for Compton scattering, except for it would. So now that I have that wavelength, 8.72 times 10 to the minus 13, was it? 17 times 10 to the minus 13. Now I want to calculate the angle for the first diffraction minimum. Well, I have sine theta 1 is equal to 1 times the wavelength over d. Therefore, theta 1 is equal to inverse sine of lambda over d equals inverse sine of my lambda 8.72 times 10 minus 13 meters over d, which is 1.00 times 10 to the minus 3 meters. So theta 1 is equal to 4.996 times 10 to the minus 8 degrees. Between friends, that's 5.00 times 10 to the minus 8 degrees. Now notice this angle here is larger than that angle, which means that we have not violated the uncertainty relation in the diffraction. We could go ahead and calculate the width with geometry. If you do that, you find the width that you actually get for the first order is equal to 1.74 times 10 to the minus 9 meters. All right, so this one here clearly was some synthesis going on. Hope you're ready for the test.